number. Welcome to Mind Matters, where we explore the cutting edge of neuroscience. I'm your host Rittika, and today we are beginning a deep dive into neurodegenerative diseases, into the depths and the realms of molecular signatures, and several other patterns. Hello, Nehal. So you
Hi, thank you for having me.
It's really great to have you, Nehal. So, when we look at protein aggregation patterns in Alzheimer's, Parkinson's, and ALS, we see very distinct molecular signatures that are widely known. So, yet recent research suggests that there might be common upstream pathways. How do you reconcile with the specificity of these diseases with the emerging evidences of shared pathogenic mechanisms?
You're right, Ritika, that neurodegenerative diseases have shared common upstream failures like impaired proteostasis, mitochondrial dysfunction, and defective clearance. Yet, they differ in the protein that get accumulated. But these misfolded protein trigger convergent immune responses like activating microglia, astrocytes, and inflammasomes, leading to cytokine release, oxidative stress, and excitotoxicity. Disease specificity arises from selective neuronal vulnerability, where shared stressors intersect with cell type susceptibilities to produce distinct syndromes. So, yes, there are different molecular signatures of each disease, but they have shared pathogenic mechanism.
Right. So, coming on to the next concept of Prion-like propagation, which has revolutionized our understanding of neurodegeneration, is something which I find extremely interesting. So, given that misfolded proteins can template their own misfolding across neural networks, what does this exactly tell us about fundamental nature of consciousness and memory storage? Like, are we essentially dealing with an information corruption problem at the very molecular level?
So, yeah, prion-like propagation reveals that protein can encode and replicate structural information, but when this becomes corrupted through misfolding, it spreads across neural network like a software bug, reframing neurodegeneration as a failure of biological information fidelity. Because consciousness and memory rely on stable synaptic and molecular systems, this templated spread shows that brain's information storage is vulnerable not only at electrical but also at protein level. Philosophically, this suggests that neurodegeneration is not merely localized cell death, but an informational disease, eroding the molecular architecture that underpins cognition and consciousness.
Right. So I also wanted to touch upon the concept of cellular senescence, which is again a very pivotal topic in neurodegeneration. So if we consider that brain's limited regenerative capacity, how do you envision the intersection between aging research, which is covering cellular senescence as a part, and neurodegenerative disease treatment? Could targeting senescent cells be the key to preventing rather than just treating these conditions? What are your thoughts exactly?
So, neurons are post-mitotic by design, but that doesn't mean they are senescent. However, neurodegeneration pushes neurons to stress-induced dysfunctional state of senescence, which is same as in aging. So, aging and neurodegeneration share biology in terms of mitochondrial decline, impaired proteostasis, and chronic inflammation. So, if we target these molecular mechanisms for the neurodegenerative diseases with xenotherapeutic strategies, it could prove highly efficacious. We are moving towards finding a cure rather than just managing symptoms. So, this is a very important forefront, and also not in my work, but many scientists in Mayo Clinic, University of Minnesota in the US, and University of Queensland in Australia have shown efficacy for these therapies and are translating this work to human.
Wow, that's amazing. How translational research has taken leaps in this recent decade. So, coming into another big question of the blood brain barrier, which presents both protection and therapeutic challenges, widely known about. doing that. So, with emerging technologies like focused ultrasound and engineered viral vectors, how do you see the future of drug delivery evolving in the brain? And what are the ethical implications of potentially irreversible modification of brain permeability?
So yeah, that's a very interesting question. So as we know, blood-brain barrier is highly selective, and it is that way to protect the brain from pathogen and immune attack, but at the same time it makes drug delivery to the brain difficult. So it blocks almost 98% of small molecules and virtually all biologics, resulting in very low bioavailability. But emerging solutions, like you mentioned, focused ultrasound, engineered viral vectors, and nanoparticles has enabled targeted and non-invasive delivery to disease region, which shows promising avenue. But this has created a risk of causing damage to the human brain. If brain permeability is perturbed, it will lead to infections, toxins, and autoimmune diseases. So the question will be, is the benefit worth the cost? How can we ensure patient safety and reversibility of brain permeability whenever possible?
Right. So that was a very, very well-rounded information, Nehal. Thank you so much for coming into our podcast, Mind Matters, and thank you, listeners, to hear our podcast and to support our efforts. If you like the content, like, subscribe, and share. Thank you.
Thank you.